Hi everyone, Dajaha. I hope you are having a good time in person or remotely. I am Oguz, and today I will introduce W2GPU for translating WebAssembly CPU code to WebGPU Shading Language for the GPU execution model. So what is the abstraction paradox? So as humans, we invent abstractions or symbolic representations to extend our limited memory or limited thinking capacity. Yet these same abstractions or ways of thought, or maybe better named strategies, impose a glass ceiling on certain optimizers and runtimes. So question one, why do we create these abstractions? Among the mammals, of course, humans are famous for having the brain capacity. However, importantly, we can, of course, distinguish a human and a chimpanzee by thinking about how they can speak the language. However, when we think about the short-term memory, like when we show a sequence of cards or colors or some objects, humans tend to not excel so much in comparison to the thought capability. So what do? We chunk, we name, we language, and we create recipes to create cognitive tools. And the abstractions, of course, inherit their strengths and blind spots. And during the evolution, we started to have these helpful utilities. However, they can occlude long-range structures because we need to think about the time that we spend in the savannah and then the ice age and how we manage to survive from that and how it translates to larger functions today. Maybe which should be consisting of hundreds or thousands of inputs. However, because of our human thinking capacity, we want to have groupings, structs, and classes, and so on and so forth. And we want to make zero-cost abstractions so we can get beyond this level. However, so what is the relation to that, to programming languages and the language models? So our traditional pipelines rely on human-crafted passes, rewrite rules, and these, of course, chunk our naming capabilities. So when we think about a system which runs heterogeneously, so when we say heterogeneously, maybe having the CPU, the GPU, and maybe some tensor accelerators, we want to think each in isolation, right? Like I did my CPU process, I had my semaphores, synchronizations, and then things moved to GPU, I did some flashing, and the things became visible. But we still have this tendency to group. So the ability to write fusion passes is much less compared to working in isolation or in terms which are easy for us to comprehend. And maybe the example for this could be, CUDA is a really well-engineered stack, and MLIR is, of course, something to really deeply respect. However, we still see the promise to be yet fulfilled and gaps remaining in terms of the performance we can recover. So we see the names, functions, kernels, and the interface contracts, explicit dependencies, yet we miss the long-range fusion opportunities, non-obvious host-to-device mappings, such as the initializations, right? We write a code base and we think that, hey, okay, I had the data coming from the network, so I want to initialize on the CPU, but maybe if you could recognize some small pattern or sequence, like you could do the initialization on the GPU too, so we miss this kind of less obvious patterns. So can we, or how can we break through this ceiling? Machines or the programs or the routines developed by the computer or statistical optimizers are not bound so much by our working memory limits or naming or procedural biases or the code review, which maybe senior doesn't approve because they couldn't comprehend at that time due to documentation. And maybe bird's eye view here is that as humans and as the program authors, we can have a short recipe or intermediate representation and know how it will translate to optimized GPU program and how it will translate to optimized CPU program, and build a large parallel data set to see if we can have the computers recover some patterns which go from the CPU to the GPU execution model, which are of course really vastly different. And this will be the idea of this presentation, or W2GPU, where we have the abstractions which generate parallel data sets, which we use to train the neural models, and then we ratify some sort of verification, and use this loop to go beyond what we have been previously able to achieve. So can this actually work for real systems? Here we enter W2GPU, our concrete example today. In W2GPU, we try to translate WebAssembly text, which is just a text representation of the WebAssembly, to WebGPU Shading Language, which is the shading language for the WebGPU API, the new modern way to use GPU resources in the JavaScript runtimes, primarily the browser. And the challenge here is WebAssembly and the WebGPU Shading Language are really different beasts. Like WebAssembly is a stack-based VM with a linear memory. Of course, you can try to have some functions or similar using the macros, yet when we have a compiler output, so when we have a program, we use Rust compiler, Rust-C, or Clang and get the WebAssembly output. It doesn't look so much so as if it's a C++ function we can easily hire to the GPU type using structured code. And so we are talking about non-isomorphic semantics here. And the W2GPU approach is using a small language model to learn these robust mappings from WebAssembly text idioms to valid WebGPU shading language kernels. So when we do this training, what is the outcome? The outcome is partially yes. There are some exciting results, especially with the shorter sequences. We see compilation success, like vastly differing by the language model family, yet achieving PSNR. PSNR is like the difference between two images with compilation success. When we inspect these output programs, we see that like they are well vectorized, they are utilizing the GPU resources and things that we would ideally want a CPU to, GPU converter to handle. And one thing to keep that in mind here is that this is only focusing on the function itself. So it's not like a cross stage, it's just one kernel from WebAssembly to one kernel in the WebGPU shading language. Yet there is a significant problem. We see really good success in these short sequences, yet when the sequences start to grow, even like the medium size, the capabilities start to crumble. Like the thing that we see really successful for the small kernels completely goes away once we scale the programs more. And the results here, as you can see, is all of the models in the training run, they managed to improve their loss over time, yet depending on the language model family, we see a vastly different ending point, and it might seem small at the end here, like hey, there's like a minuscule difference, yet that minuscule difference really makes a huge difference in their capability. For example, the worst performing language model family here actually just produces gibberish, which looks like VXL code, yet doesn't compile at all. On the other hand, best performing language model families, small model performs better than the larger of the other language family models. So this is one maybe surprising result here, that a language model family really matters a lot. So the size is not the only thing, but the pre-training and the architecture used really has an impact. So if we look at the output here qualitatively, in the good example, we can see just it's just basically identical. In the other case, we see that because this is not trained on the output of the kernel, so the language model trained never sees the pixels, but just sees the routine. We see an encouraging preservation of the algorithmic steps to produce stripes. Because otherwise, if it was trained on the image output, we could maybe see gray here, because when we have these stripes, the average is gray. So if it just learned on the output of the image, maybe it would produce a gray, but here we see some encouraging fail case. So it's a failure case, of course. However, it is encouraging that it learns the recipe and not just the output. And here we see the similar thing. The circles are like, well, to our eyes, they might look identical, but they're not, slightly different thickness, etc. And on the bottom row, we again see the same encouraging pattern. The color, etc. is different. However, routine is preserved. So that is the one output that we observe here. So to talk slightly about the background of the W2GPU, W2GPU has been actually in development for a very long time, and I have first tried to do with like traditional compilation passes, etc. However, over time I started to notice that if we just use the traditional passes, then it just starts to become a cookbook. Hey, use this macro here, add this command there. You are not writing the code correctly. Like it's like instructing the person who wants to use C++ for the GPU to use C++ in a restricted way. So I never felt satisfied yet. This last year, I have been experimenting with language models and found this encouraging output. And because this is the initial run of the LMPL, I wanted to touch upon like why I submit this work here. I think it's a very critical venue for empirical programming languages. So for the natural language processing people here, like who might have familiarity, empirical natural language processing is an important concept where you are not in the charge of the things, but you can only observe things. So over time, as we have these neural passes, ways to define the program recipes, it will become more important to see like where they fail, where they succeed, and it might be important to treat them as like empirical category of the programming languages. And I think LMPL can be a good place to share data sets, validators, evaluation protocols, and see how much work can be reused across the research and maybe industrial tools. And I'm highly honored and grateful, and really appreciate the organizers and the reviewers' effort to bring this venue to life in, I guess, quite a formal field, programming languages. Like it's quite a good work, so thank you. And also thinking about the LMPL, and maybe for W2GPU, long-term vision is achieving one recipe, but taking it to any heterogeneous system in the most optimal way without thinking about which resource should be allocated on which field. But it's just a long-term vision, and we are running slightly short on time. And the practical impact from W2GPU is for developers. You can just, if you have a small kernel, you can start from the LM drafts rather than writing the GPU kernel by hand from scratch. And for researchers, we will be opening the adapters and the recipes, so it can be a starting point for you to do your own experiments with your own data sets. And the key takeaway here is we have certain limits, driven by our abstractions, and the parallel data sets can reveal certain transformations beyond like what we have been able to do so far with handcrafted rules. W2GPU shows feasibility, yet also strong failure cases. And the contributions are more than welcome. I will open source the W2GPU entirely, and I will be more than glad if anyone wants to do things together or add to the discussion. I'll be really welcoming it. And eventually it will be good to have a reliable compiler passes. And I would like to take one page to acknowledge all the open source community for building these tools, and also, of course, all the researchers who have, done their best to use the scientific method to take a record of what they have done. Thank you very much, and it's standing on the shoulders of the giants, so I really appreciate all the community here. And a special thanks to LMPL organizers for launching this venue. And these are the references. And I will be opening a release in the early next year. Do we have some time, or are we sure?
We have time for questions. Maybe one or two questions.
Okay. So while we take the questions, you can maybe take a look at this page as tips and tricks in case you haven't been into training the language models, like how we can start small and do it, because I think some of the audience is just PL background. So please take a moment to have a look, and thank you. Okay, I can take a question if that is okay. Thanks so much. Everybody.
Please use the microphone for questions.
Hi, Nice talk. I had a question. you're looking at WebAssembly to WebGPU, and mostly this looked at, I guess, just like correctness of whether or not you could get it to compile. Do you think there's like specific reasons why you'd want to do WebAssembly to WebGPU, like for performance, or did you see like specific algorithms that might benefit from this?
That's a really great question. My reason for WebGPU is actually sandbox, because for the GPU we don't have really great virtualization, and WebGPU runtimes do their best to isolate the processes and do something above what the drivers provide, so we don't need to pay licenses for like a partitioning one GPU into multiple users. So that is the primary reason. Thank you very much. I appreciate it.
All right, let's thank the speaker again.
Thank you very much, everybody.